Hi everyone, Professor Robert J. McEwen here. Welcome to another video in our course on calculus, mathematics for economics. We are now into the final stretch and we're going to be talking about integration. Now most of you have not seen integration before. It's not included in most high school curriculums. And so it's going to be new to you. We're going to go through it very slowly together. We're going to go through it carefully. And we're going to keep things as simple as we possibly can. Now, up to this point in the course, we've been taking derivatives. So you're going from one function and then looking at its slope and analyzing its slope. And we can do all sorts of things, as you saw in chapter 7 and 8, all kinds of applications for derivative calculus. What integration is going the opposite way. What if we can go from the slope to the function itself? Or maybe we want to calculate an area. So integration was really invented for calculating areas. So we'll talk about the Babylonian problem. Now I hope you're ready. You've got your pencil with you. You've got some paper with you. Otherwise you've got an e-pen and a writing tablet. I hope that you are ready to go. And if you are, keep watching. And by the end of it, you're going to have, I hope, a decent understanding of what integration is all about. What is integration? Well, integration is sort of the opposite of taking the derivative. And that's why it's called the antiderivative. Now, let me illustrate with an example. I can show you a little bit about what integration is used for. So suppose that we have a function f of x which is equal to 4. If I was going to draw that on a diagram, it wouldn't be very exciting. On the y-axis, I have f of x. I've got x on the x-axis. And then where 4 is, we're just going to get what? We're just going to get a horizontal line. And it's just going to go on forever. And basically it's kind of saying, well, if x is, say, 2, f of x is going to be 4. If x is 99, well, f of x is still equal to 4. Now let me ask you a question. What function has 4 as its derivative? So can you name a function that has 4 as its derivative? Well, I hope you came up with the answer of 4x. And maybe I'm going to call this capital F of x. 4x. Now, I don't know for sure if that's the actual function that I know that this function has the derivative 4, but there could be some constant term here, right? If I added 100, then f of x would still be the derivative of big F of x. So I don't know what this constant term is. If I made it 50, well, it would still be true. If I made it, negative 1,000, it's still going to be true. All right, now we'll come back to that a little bit later when we formalize things. But looking at this graph, I've drawn the function little f of x is equal to 4. Now I know that its integral, its antiderivative, is 4x. Right? And we could write capital F prime of x is equal to little f of x, which is equal to 4. Now, if I told you that, let's say, x was equal to 3, and I go back to my diagram that I've drawn over here, and I put a 3 here, and I walk my way up. Now I want you to evaluate f of x is equal to 4x when x is equal to 3. And if you do that, you get big F of x, big F at 3 is equal to 4 times 3, and that's equal to 12. Right? So you've done that before. You've done that many times already in this course. Now let me go back to the diagram, and let's see something about integration by looking at this diagram. If I put 3 on the x-axis, and I walk my way up to the function little f of x, notice that I've got a 3 and I've got a 4 here, and well, 3 times 4 is equal to 12. And if I wrote 1 and 2 here, 3, 2, and 1 here, I'm going to get, well, 12 little boxes, 5 little, or I should say 12 little squares. So what can you take away from this? Well, a couple of things, and we're gonna talk about them in the coming videos. Integration is related to areas, to finding the area. It is also related to the area beneath the curve, in this case f of x. Maybe we can just put a comma there. So we took the integral of 4 and we decided it was 4x. It could have been 4x plus 25 minus 25. We weren't sure about that constant term, but the 4x we could agree on. And we also happen to notice that if I put in a value for x of, say, 3, I find the area underneath the curve. And we're going to talk a lot more about that a little bit later. So to give you a little bit of idea where we're going, you can think of integration as being very similar to multiplication. You know, one mathematician referred to it as the big guns of multiplication. So if you're trying to find the area of a complicated curve and just simple multiplication won't do it, integration can help you. So let's take a look at this slide. It's integral notation, so we're going to learn something about integration. And this is a indefinite integral. And that's so important, I'm going to put my highlighter across it. This is an indefinite integral. What do we mean by an indefinite integral? Well, we're allowing x to take on any value. So we're essentially evaluating this function from any value of x where the function itself is defined. And that we don't bother to write in those infinity signs there. We just draw it like this sort of squirrely shaped. Sometimes people say it's, you know, kind of an S shape, barely an S shape, but it is kind of an S shape. And well, I could go on and say something about an inflection point, and it's concave at one point and convex in the other, but that's enough. Now, if we want to integrate the function f of x, our notation tells us, okay, well, you're going to integrate with respect to x. That's this dx here, the difference x. And it's going to give you this new function that we're now going to call big f of x. Now, well, the prime notation will come back later, but for now, we don't have any prime notation here. You know, you could be finding the integral of a derivative, or you could just be finding the integral of some function. And so here we've got it written like you're finding the integral of some function little f of x. And one of the problems with integration and why it's challenging, it's actually really quite difficult. I'm going to try and go very slow and do the things that are more straightforward, certainly the more straightforward things first. One of the things why it's difficult and challenging is we can't really be 100% certain of the answer. We knew that f of x was equal to 4, but big F of x could be equal to 4x plus 5. It could be minus 100. We weren't sure. We weren't really sure. And so whenever we integrate, we have to add this constant c term. It's some unknown constant c. Now, how do you use this notation? Well, suppose I have my integral sign like that, and I have 4. Remember, f of x was equal to 4. It's rewritten right there. D of x. So I realized we don't really need these. In fact, we don't want those brackets there. We'll just write it as d of x. And this is going to be equal to big F of x plus c, which is going to be equal to 4x plus c. And so that's how we use the notation or that's how we understand the notation. Here are a couple integrals. See if you can find the antiderivative for these two very simple functions. Press pause, give it a try yourself, and then when you're ready, start up the video again and I'll walk you through the solution. So at this point you're not supposed to know any rules, so you're just giving it your best. Looking at A, this looks like it would be equal to x squared. Right? The derivative of x squared is 2x, and I never want to forget my constant term. Right? This is the unknown constant. I don't want to forget that. And just to keep in mind, if you forget it on a test, you will lose marks. And I remember when I was an undergraduate and I was learning integration, and on the test I would always forget the c, and I always lost marks. But you have to remember the c, make sure you put down the c, and you remind yourself that there's always this constant term that we can't be sure of. Now what about b? B's a little trickier. So x squared, that part is a little more straightforward. There's got to be a 3 up there. And then, well, we know the power rule says the 3 has to come down. So 3 times something has to be equal to 2. And so if that something is equal to 2 over 3, let's try it. Let's take the derivative of this thing. The 3 comes down. We've got 2 over 3 x squared, and then the 3's cancel out and we're left with 2x squared. So I used a little bit of algebra, and I found that the integral of this thing right there is going to have to be this thing.